Several years ago, I attended a math conference and someone gave a presentation on the game of Spot It. Now, I'll confess I don't really remember the main result of the presentation, just a few details about the cards and the gameplay itself. Last spring, I thought it would be fun to get several decks of these cards, bring them into my discrete mathematics classroom, and we could explore some of the properties. However, COVID hit, and so I decided maybe we should make a video of this instead. How do we play Spot It? Well, there are several ways to play it, but one way is to give each player a card. Now here we have 6 players. Then we're going to take another card, place it face up in the center. And at this point, the players scramble to see which picture on their card matches the picture in the center. If you want to try this out, you might want to pause the video and see if you can find the matching pictures for each of the cards. We'll go ahead and show what they are. So in the center one, with the top card, we have a matching taxi cab. For the second one, we have a slice of cheese. The third one, it's hard to see what it is, and it's a little hard to even know what it is. I think it's a paint splotch. Then we have a fire on the next one, and an igloo here. And for the last one, you might say it's a dolphin, but that's not correct. It's a common porpoise. What I do remember from the presentation is that regardless of which pair of cards you pick, there will always be a matching image between them, and only one, which is really kind of a fascinating mathematical construction. How could you come up with something like that? The question I thought that I could work with on my students was, how many different images are there? Now, of course, you could go through and catalog them, and I'm not going to say I did that because that would be embarrassing to admit that. But you could catalog them and see how many there are, but we're going to use mathematics to come up with this answer. We need some facts about the cards. First of all, there are 55 of them, which you can get by taking a tin of the cards and counting them out, or you could look at the tin and it says contents 55 cards. It's also easy to see that there are 8 pictures on each card. In order to do our calculations, we're going to need to make some assumptions. The first assumption we'll make is that every image appears on the same number of cards. Now, I do want to distinguish between an image and a picture. A picture is a physical representation of one of the abstract images. Okay, so there will be far fewer images when we're done than there are pictures. We'll talk about the number of pictures here shortly. But we're going to assume that every image appears on the same number of cards. So if the igloo appears 12 times, so does the fire, so does the wedge of cheese, and so forth. For our second assumption, we need to make an observation first. First, if I have any pair of images, let's say we have the Sierpinski triangle and the Mandelbrot set, they might or might not appear on some card together. We don't know. But we do know that there can't be a second card that has these 2 images on it. Because if there were another card like this, and the card on the left was the center card, and the card on the right is my card, then I have 2 ways of winning this particular card, because there would be 2 matching pictures, and that violates the 1 matching picture condition. So there can't be 2 cards with a pair of images on it. So there are either 0 cards with a given pair of images or 1 card. And we'll be optimistic. We'll assume that each pair of images appear together on exactly 1 card. These 2 assumptions will allow us to start doing some calculations. Here I have my own designed Spot It card with some math symbols. It has 8 pictures on it. With 2 cards, we would have a total of 16 pictures. Now remember, there are 16 pictures but 15 images. And what I want to do is I want to imagine that I'm going to do something destructive and cut out the pictures from the cards. Now let's see what would happen if we did this with the entire deck. With the entire deck, there are 55 cards. There are 8 pictures per card, so there will be 440 pictures overall, 55 times 8. Rather destructive, but it would help us solve our problem. Now let's do some organizing with these pictures. Let's take all the pictures of the same type. We know that every image appears on the same number of cards. So we'll take all the Sierpinski triangles, line them up. Take all of these crazy little squares, line them up. Keep going until we get to the trefoil knots, and then finally the dragon curve, and we've got them all lined up. Now we know some things. We know that each of these images appears the same number of times, but we don't have a way to represent that mathematically. We also don't have a way to represent the number of images, so let's say that there are n images, and that each image appears d times. Now here we have a nice little rectangular array that has d rows and n columns, so there are n times d pictures overall. But remember, on the previous slide, we said there were 440 pictures overall, so we have an equation now. N times d is equal to 440. Now we're regretting our decision. We decided to cut all the pictures out. Let's suppose we have some regret and we want to glue them back on. And we're going to use the assumption that every pair of images appears together on some card to come up with a second equation. Let's suppose we want to put the Sierpinski triangles back on cards. So we get enough of those little circles and we glue the Sierpinski triangles back on. All of them have been glued back on, and now we need to put the other pictures back on. Well, each card has 8 pictures, so we'll have to add 7 other pictures to that card, and to that card, and to each of the remaining cards. Let's do some mathematics with this. We know that the Sierpinski triangle appears d times, which means there are d cards overall. Each card got 7 other pictures, so there are 7 times d pictures that we glued back on, not including the Sierpinski triangle. What pictures did we glue back on? Because the Sierpinski triangle is paired up with every other picture, we glued on all of the other pictures. If there are n pictures total, then there are n minus 1 other pictures aside from the Sierpinski triangle. So 7 times d is equal to n minus 1. And now, as all good algebra students do, we have 2 equations with 2 unknowns we can solve. So we've got n times d is equal to 440. I've highlighted the d because we'll substitute something in for that later. 7 times d is n minus 1. If we take the second equation and divide by 7, we get d is n minus 1 over 7, which we can then substitute into the first equation. I'm not a big fan of fractions, so I can multiply both sides by 7 and get n times n minus 1 is 3080. Now we enlist our favorite algebra student and say, hey, here's an equation for you to solve, and they say it's a quadratic equation. I know how to handle those. We'll distribute the n minus 1 through, then we'll subtract 3080 from both sides. I'm not good at factoring this guy, so I'll resort to the quadratic formula. No. I tell you, we don't need that. Let's look back at the equation that we had. N times n minus 1 is 3080. N is an integer, right? So n minus 1 is another integer that's 1 less than it. We're really dealing with 2 consecutive integers whose product is 3080. So it's more of a puzzle than it is an algebra problem. Well, I claim that we actually shot ourselves in the foot earlier by doing some calculations. Where did the 3080 come from? It was 440 times 7. But 440 arose from a calculation as well. It was the number of cards, 55, times the number of pictures per card, which was 8. 8 times 7 is 56, and we have 2 consecutive numbers whose product is n times n minus 1. That must mean that n is equal to 56, so there have to be 56 images. Cool. So we could stop here, but we're curious, folks. So what we'll do is we'll calculate how many times each image appears. That's the equation d equals n minus 1 over 7 with n equal to 56. We find out that every picture appears 55/7 of a time. Something's not good here. Now, all of the equations that we established were good equations. The logic was sound. Where did we go wrong? Well, we must have gone wrong with our assumptions. So one of these assumptions, at least one of them, must be incorrect. The first one is that every image appears on the same number of cards. That was the value d, and d seems to be wonky, so that must not be true. Well, let's reflect on our number. 55/7 is a number between 7 and 8, pretty darn close to 8. Maybe some images appear on 7 cards, some of them appear on 8 cards. I hate to do this, but we'll introduce a couple more variables. We'll let S be the number of images that appear on 7 cards, and E be the number of images that appear on 8 cards, and we can establish an equation very similar to what we've done before. Let's take all of our images that appear 7 times. There are, we said, S of them. It's a rectangular array, so there are 7 times S pictures over here. Let's take all the images that appear 8 times, line them up. They appear 8 times, there are E of them, so there are 8E of these pictures. And remember, there were 440 pictures overall, so 7S plus 8E is equal to 440. Now, We also have an equation that we can establish because S plus E is the number of images, and we calculated the number of images that was the value n. We think it's 56, so we can set that equal to 56. Now we have more equations to solve. S plus E is equal to 56. If we subtract E from both sides, we'll get S is 56 minus E, which we can then substitute into the equation 7S plus 80 is 440. If we substitute that in, do a little bit of distribution, and then we can collect like terms. We have 392 plus E is 440. Easily solve for E by subtracting 392, and we find out that there are 48 images that appear 8 times a piece. And S is 56 minus E, which is 8. So there are 8 images that appear 7 times a piece. Nice. Well, now that number 8, wow, that number 8 images that appear on 7 cards, that's kind of a significant number. Isn't 8 the number of pictures that appear on each card? Maybe our second assumption was also false. And the second assumption was that every pair of images appear on some card together. Well, maybe these 8 images don't appear on some card together. Let's say these are the images. That would mean that our other assumption was wrong. And if none of these are paired together, then we could make a new 56th card with these 8 images. Awesome. So now we've increased our deck size. Let's see if the mathematics works out now. 56 times 8 is 448, so there are 56 cards instead of 55 now. We've added 8 new pictures. N times D is equal to 448 then instead of 440. Our other equation, 7D equals n minus 1, still holds. We substitute, multiply both sides by 7, and we get n times n minus 1 is equal to 3,136. Once again, no algebra here, it's a puzzle. Find 2 consecutive numbers whose product is 3,136. Well, we can do some number checking, right? 56 times 55 is 3,080, so it shouldn't be too far from this. Let's just go up one. 57 times 56 is 3,192, already too big. For those of you who might be curious about the solution to this equation, it's approximately 56.5. Let's review what we've done. We made some assumptions. We did some calculations based on those assumptions. Didn't work. We thought, well, maybe we could add a card. Maybe it's not just one card that we could add. Maybe we could add several cards. Maybe it's the number of cards that is the unknown. The other problem is that we all built this on the assumption that there were exactly 56 images. Maybe that wasn't right because some of the things fell apart. Maybe our calculation getting the n was 56 was faulty as well. So we need to scrap everything and kind of start over. Let's suppose we have C cards. We know C is at least 55. We don't think it's 56, but there would be some more cards that we could add to the deck. In this case, n times D, the number of pictures overall after cutting them all out, would be 8 times C. Still have the 7D equals n minus 1 equation, which we can substitute, and we can multiply both sides by 7. So we've got to guess, what value of C will work? We want 2 consecutive numbers, n and n minus 1, whose product is 56 times C. We already tried to let C be 55. That didn't work. Well, 56 is consecutive also with 57. So what if we did 57 times 56? That would mean the number of cards should be 57. The number of images, n, would also be 57. And does D check out? Well, D was n minus 1 over 7. 57 minus 1 over 7 is 8. Every image would appear 8 times. Is this it? Did we stumble upon it? And it turns out that yes, there should be 57 cards, but only 55 of them are included with the deck. 2 of them are missing. You could construct these extra 2 cards, throw them in, and play along. There are 57 images. I calculated them or I cataloged them. They're there, trust me. Every image appears on 8 cards except the images that appear on the 2 missing cards. So let's imagine that these are the 2 missing cards. There are 16 pictures overall, but only 15 images because the Sierpinski triangle appears twice. So any image that appears on one of these two cards won't appear 8 times. It will only appear 7 times, except for the Sierpinski triangle, which only appears 6 times because it was missing twice. So we could set up some equations like we did before. Overall, taking out these 15 images that are missing from the 57, there are 42 of them that will appear 8 times. Earlier, we let S be the number of images that appeared 7 times and E be the number of images that appeared 8 times. We could let H, standing for hex, be the number of images that appear 6 times. So 6H plus 7S plus 8E should be the 440 pictures. 6 times 1 plus 7 times 14 plus 8 times 42 is 440. So the mathematics works out. How did we get here? What kind of mathematical structure allows us to do this? Well, it's based on something called a finite projective plane of order Q. And they have the following properties. Every pair of points determines a unique line. That is, every pair of images appears on some card together. So the cards are acting like lines. Every pair of lines determines a unique point. Every pair of cards has a common image. Now there's a third condition, which we really don't need to worry about. It just prevents us from having trivial kinds of things. We can find 4 points that no line passes through more than 2 of them. Okay, that's just preventing us from having projective planes that don't behave like we want them to. There are some nice little facts about projective planes. If the order is Q, there will be Q squared plus Q plus 1 points. Q squared plus Q plus 1 lines, so the number of points and lines will always be the same. Every line contains Q plus 1 points, and every point contains Q plus 1 lines. Okay, so our example, our Spot It game, is an example of a projective plane or based on a projective plane of order 7. 7 squared plus 7 plus 1 is 57, which is equal to the number of cards and the number of images. And 7 plus 1 is the number of pictures per card and the number of times each image appears on some card. So it's really kind of interesting that this deep, rich mathematical thing called a finite projective plane could be used to create these Spot It cards. Well, it turns out that you could create Spot It cards using any finite projective plane. So we'll end the video with just a quick demonstration of how you could do this with the smallest finite projective plane possible. And that's of order 2, and it's called the Fano plane. Here is a nice picture of the Fano plane with 7 of my images. Each line could then be used to create a card. So I'm going to create a card with the Sierpinski triangle, the Mandelbrot set, and the trefoil knot. Turns out that there are 7 images. There are also 7 lines, which means we could come up with 7 cards. Where do the other lines come in? Well, you've got the 3 edges of the triangle. If you start at the Sierpinski triangle at the top and go straight down through the Venn diagram and to the sigma sign, that would give you another line, and there are 3 lines of that type. And then there is this line that looks more like a circle, but that would be the 7th line. So it's really fascinating that something so rich, so deep mathematically as a finite projective plane can be turned into something fun that even young children can enjoy.